Assignment 1, I put up a chart which had the ages of the presidents at their first inauguration. And I'm going to open that up. And there was a problem with the chart. It was only 44. The question asked about 45, and so on and so forth. This is a correction of it. Now, on the assignment, I just changed it so that any answer you gave you credit for it correctly. Because once you started answering that particular question, I couldn't delete it, and it wasn't very easy for me to modify it. So I just made it so that it gave everyone credit for that. But let's take a quick look at that problem right now. Okay, so this is the chart, right? I think it shows 45 presidents, right? I'm going to count them: 2 and 7 is 9, and 13. Did I get that right? 7, 2, 9, and 13 is 22, and 12 is 34, and 7 is 41, and 3 is 44, and 1 is 45. So there's 45 presidents listed here. Okay, so I also made a little chart over here of the age ranges and the frequencies, right? This table is this bar chart, this histogram really, is a chart which demonstrates the distribution of these different ages in different groupings, in bins. So if you're between 40 and 44.999, you're going to be in this bin. If you're 45 to 49.999, you're going to be in this bin, and so on and so forth. So 50 to 54, there are 13 presidents that were that age when they were inaugurated, according to this chart. You know, I'm not going to vouch for its absolute certainty, but you know, like that's basically what we're looking at. So the idea here is that we're getting a little bit of practice with histograms, right? So this histogram gives us this distribution. That kind of looks like a normal distribution. We're not up to that yet. We'll be talking about that starting on Monday, right? So we have this special kind of distribution that we're working with. Okay, whoops, I didn't mean to. Let me see if I can alter the view here so I can get that down to the size I want. Okay, let me see if it's available here. Yeah, let me go back down to, whoops. Okay, I think that's big enough for us to be able to read. Okay, so let's take a quick look at this. Now, if I were to ask you how many presidents at their age of inauguration was between 60 and 64, or 60 and 64.999, right? You'd say to me, well, I just can go to histogram here and see the height of this gives me the frequency. That's the way histogram is going to work, right? The y-axis is the frequency, the x-axis is the range or bins, right? So there's going to be 3 presidents in that range, right? There at 70 to 74, it shows 1 president as being in that age range. In reality, there might be 2, depending on how you look at it. I think this is first inauguration, right? Because Reagan was over 70 for his second, so he's not included here because he was 69 during his first inauguration, right? So this would be Trump, obviously, because he's the one that's in that 74 age. Okay, if I ask you, if I randomly pick a president from the 1st to the 45th, what's the probability that they would be under 50? Okay, let's think about that. So the probability it would be under 50, well, there's 45 presidents here, right? How many of those are under 50? Well, we have 7 here. Oops, this doesn't want to cooperate with me. So let's go back again a little bit. Let me go back to 150. Okay. So there are 7 presidents in 45 to 49 age range, and there's 2 in 40 to 45. So I have 7 and 2, 9 that satisfy that criteria under 50. So the probability of my randomly selecting a president under 50 is going to be equal to 9 divided by the number of presidents, number of different outcomes, and that's going to be equal to 20%. Right? So what's the probability that if I randomly chose a president, that they would be between 50 and 59.99. Okay, well, how many presidents are there in that age range? Well, there are 13 plus 12, there are 25 that satisfy that criteria. So that's equal to 25 out of 50, out of 45. And that's 50, above 56%. There's a probability that I would choose a president randomly that's in that range. Now, let's take this a step further. I'm going to ask you about something that's called a conditional probability. Now, we talked about Bayes' theorem and conditional probability. So conditional probability, let's see what that might look like. Okay, one of the ways that might look, and I'm going to type this in rather than write it in so I can get away with it. What's the probability that a president is less than 50, No, actually, let me do it this way. What's the probability that a president is greater than 65, given, I'm going to use this symbol called a pipe. It's a straight up and down line. Okay, if I can find it on this particular keyboard. Yeah, there it is. Okay, great. Given that we're only considering that we know that the president that we're selecting is over 50, is greater than 50. What's the probability, given that we're selecting a president that's we're only selecting among presidents who are over 50, what's the probability that he's over 65? Well, how many presidents are over 65? So we have 3 and 1, we have 4 presidents. 4 presidents that are over 65 divided by, well, now our criteria is not 45 anymore, right? It only includes the ones that are over 50. So that's going to be 13 and 12 is 25 and 7 is 32 and 4 is 36 out of 36. Actually, so that's 11% is the probability that I would randomly choose a president over 65, given that we're only looking at presidents that are over 50. Conditional probability. That condition has to be satisfied first before we could determine what are our possible outcomes. Are you guys okay with that? Does that make sense to you? Everybody comfortable with that? That's simple conditional probability. We're going to get into more complicated versions of conditional probability in just a little bit because we're going to talk about Bayes' theorem. I just want to get a formula available. How should I do this? Let me see if I have a Bayes formula. Let's see if I got a picture of it here. There we go. There it is. Okay, let's open that up. Okay, so this represents Bayes' theorem. And what does Bayes' theorem say to us? It says the probability, the conditional probability, that A occurs, given that B has already occurred, is equal to the probability that B occurs, given that A has already occurred, times the probability of A over the probability of B. Well, you might say to yourself, well, how does that help me? How am I going to use that thing? What good is that? I mean, where's that going to come in handy? Well, when we talk about diagnostic testing, this is going to be a relationship that's going to be of some value to us. Okay, so let's say that now we'll get a positive test for a disease, right? What's the probability that you actually really have the disease if you get a positive test? So let's call A the probability that you have disease, and B the probability that you've gotten a positive test, the fact that you've gotten a positive test. So basically, this says, what's the probability of having the disease given that you've tested positive, right? Okay, so let's see what this part says. Probability of B, given that you are A, that A has occurred. That's the opposite. That's the probability that you get a positive test, given that you have the disease. Well, if you guys have looked at the session where we talk about sensitivity and specificity and positivity value, you know that that is the sensitivity of the test, right? So sensitivity of the test is the probability that you test positive given that you have the disease. So let's say it's 80%. right? That sensitivity is 80%. 80% of the time it correctly identifies people that have the disease, times the probability of having the disease. This is the prevalence. So it's the sensitivity times the prevalence here, right? Well, what is that? Well, this is the percentage of people in the population. Let's say it's 10%, right? And this is the probability that it will correctly identify the ones that have the disease, and 10% have the disease correctly, which is 80%. So 80% of 10% is 8%. So 8% of the people would test positive and have the disease. And what is the probability of B? Well, probability of B is the probability that you've tested positive. So you have the percentage of people that test positive and have the disease over the percentage of people, probability of testing positive, or the percentage of people that test positive. So this is your positive predictive value. In other words, this is the certainty that you have the disease. This is the probability of testing positive if you have the disease, and this is the probability of testing positive overall. So if this comes out to 8%, and the probability of testing positive is, say, I don't know, 20%, and you know what the probability that you actually have the disease is, you've been tested positive. We're going to work with a more friendly version of this for you guys. So if it didn't get through completely right now, don't worry about it. It'll make more sense just a little bit. Okay, so let's go to the questions that I got online. So guys, remember, if you want to type in an additional question like that, actually you didn't see that because the student actually just directed it to me, so you didn't get a chance to see the questions there. Okay, but if you want to type it in, you can, you don't have to be shy. You can type it in, or you can just direct it to me, and I'll address the question. If you don't want to share it with the rest of the group, I'll repeat some version of it so you know what's being asked. Okay, so let's take a look at the homeworks so that we can kind of skim through what we're doing here. Let me just see some. There's a question on assignment 1. There's on assignment 2. Okay, let's go to assignment 1. I think I have it here somewhere. Okay. Let me pull this up over here. Okay, I guess this is it right here. Okay, assignment 1. I got a few questions on the discussion boards about the idea of going over the data types. Data types are going to be important to us later on in the semester because depending on what kind of data type you're working with, that will determine what statistical test you should apply. So, for instance, if you drill a hole in a piece of wood and you need to put a screw in it, you need to use a screwdriver. Hammer ain't going to help you, right? And a wrench ain't going to help you. You need a screwdriver, right? But if you have a nail, you need a hammer. Your screwdriver is not going to help you, and so on and so forth. It's a pretty dumb analogy, but it really applies here. So if we have certain kinds of variables, if we have numerical scalar variables, we're going to wind up applying statistical tests that, say, a numerical variable like blood pressure. We want to compare the blood pressure of Americans to the blood pressures of Frenchmen. And we want to compare that. So those are both numerical variables and numbers on a scale, right? So we would be comparing the means. We want to compare the mean of one group to the mean of another group. There's a test for that. It's called a t-test, right? There's if we wanted to compare blood pressures in New York City to different ethnic groups, those are mean of this group, the mean of that group, the mean of that group, the mean of that group. You can do those all at once using something called ANOVA. That's called ANOVA, right? And let's say that we wanted to see if there's an association between using IV drugs and having HIV, being HIV positive. Well, those two are categorical variables, right? Because let's think about it. HIV status is either positive or negative. It's either a yes or no. Using IV drugs is either a yes or a no. Just like gender would be male and female and so on and so forth. Those are categories or nominal variables, names, basically, right? So when we want to see if there's an association between those two, we use a test called chi-square, or we use a test called odds ratio, and so on and so forth. So for each of these different categories of variables, we're going to apply the right test. We don't want to use chi-square for evaluating whether two means are the same, because we use t-test for that. It's like using a screwdriver in place of a hammer in this case. So that's what we're after. So it's important for us to wrap our heads around this. Okay, so let's take a look at this. Now, one of the things that came up, and I'm going to open this up also. So I got a scratch pad here back here that we can use as well. Okay, so let's take a look at this. Rather than go through these questions, I'm going to take a look at each one of them. So what kind of variable is what is your country of origin? Well, your country of origin is going to have a name, right? It's not a numerical variable. So that's a categorical variable. It's got a category. France, Italy, Mexico, Honduras, wherever you're from, that would be a name. Categorical variable, categorical nominal basically mean the same thing. Right? They're describing the same kind of data. It's good, thank you. I like when people chime up there. Categorical. Okay, how many siblings do you have? Is that a numerical variable, categorical variable, ordinal variable? I'll get to ordinal variable in a second. Anybody have an opinion on that? Okay, how many siblings do you have? That's a numerical variable. Now, one of the questions that came up is, somebody noticed that we also sometimes refer to that kind of variable as either, whoops, what did I do there? As either, let me get rid of this. We often refer to that kind of variable as numerical, but we kind of break that up into two categories. We call it either numerical scalar or just plain numerical. So a lot of times you won't bother to specify scalar. And we call it discrete. Discrete typically refers to when we have data where you're doing a count. Like, so for instance, in this question, the question was, how many siblings do you have? So it's numerical, but it's numerical discrete. You're not going to have 3.5 siblings. You're going to have 2 siblings, 3 siblings, 5 siblings, and so on and so forth. And I'm not going to get into, I'm trying to avoid getting into the whole discussion of, well, maybe there's a way you could get half brother. We're just talking about total humans that we're counting, right? So now it's very commonly used to describe. Now, chances are you may not be changing the way you handle the data that much, right? So there's a lot of kinds of discrete data. For instance, number of siblings. How about population? Population of small towns in the United States, 3,128. Population of another small town, 234. Right? Well, you can kind of look at that almost like scale. I mean, they're big numbers. It's not like 2 or 3. I wouldn't get hung up on this too much, right? So basically, if it's a count, you can call it numerical, discrete, or you can just call it numerical. I could live with either one of those. But scalar is kind of special. Scalar indicates that there is a scale involved, like 0 to 1,000 or something like that. Let's look at blood pressure, for instance. Blood pressure is measured in millimeters of mercury, how much weight of mercury that it'll hold up, right? So when you say someone is 80 over 100 over 80, did I do that right? The other way around, 80 over 100, 100 over 80, you're talking about millimeters of mercury, right? So now, really, in real life, nobody's exactly 80 millimeters, right? They might be 80.02, might be 80.1, but a doctor's not going to bother with that. He's going to put a whole number down there, right? So that's not really, it looks kind of like a discrete variable, discrete numerical variable. It's not really discrete, right? It's really on a scale. You talk about weight, right? You weigh 213 pounds. Well, no, probably it's very rare to find somebody who weighs exactly 213 pounds. They could be 213.0001 pounds, for instance, right? So that's on a scale. That's a scalar variable, even though our significant digits is only 3, and we're only counting those 3 digits. We understand that it's scalar. So numerical discrete refers to basically integers, where you're counting things. Numerical scalar refers to when it's on a real kind of scale, right? But I wouldn't get too hung up on the difference with that. I know it's a little concerning and stuff like that. On an exam, I'll make it really clear. So I'm not going to ask you, I'm not going to tell you, well, the population of New York City is 8,943,562 I'm not going to ask you if that's numerical, scalar, or discrete. I'm just going to expect numerical for that. But if I ask you how many cups of coffee did you drink today, and the answer is 3, for instance. How many whole cups of coffee did you drink today? And the answer is 1 or none or 3. That I would consider discrete. So you might get that question. So going back to this, do you smoke? What kind of variable is that? Okay. That's going to be a categorical variable, right? Because you either smoke or you don't smoke, so yes or no. If I ask you how many cigarettes do you smoke a day? Well, that's a numerical variable, right? So you might consider that to be a discrete numerical variable. If I ask you how many cigarettes do you smoke on average over the course of a week, well, on average now, gee, if you keep track, 10 to 10, you might be smoking 93.2, right? So it might be scalar, right? There you go. How many comes to okay, what is your blood pressure? That's, again, numerical variable, scalar in this case. How would you rate the MPH program? Excellent, good, fair, or poor? I'm not asking the question. I'm just asking what kind of variable it is. Anyone who has a guess on that? This is a little bit different. This is a categorical variable, right? It's categories, but it's a special kind of categorical variable. Ordinal, exactly. It's ordinal because it has order. In other words, the values can have some variability in them. In other words, for instance, the difference between excellent and good might be different than the difference between fair and poor, right? In other words, you might have a little wider range there. Or one student's response good is different than another student's response good, right? They might have different criteria, right? And then the classic of this is the pain scale. One person's level of 6 on pain could be somebody else's level 4, and so on and so forth. All you know is that it has order. In other words, that person would have said says that it's more than good or less than fair or something like that. So you could see it has some order, even though it's a categorical variable of sorts. Right, so you can go through the rest of it. They're all really the same variables. I think they don't change as you go through the rest of the stuff. But you can pick out the answers for that. Okay, so okay, so that's the one that got my. Oh, we just did that, right? We just ran through that one, right? I kind of changed that. Oh, okay, so I did. All right, there's a couple of things I didn't ask you just now. What proportion? But I asked you which bin contains the 25th percentile and the 75th percentile, and I'm going to add to that the 50th percentile. So let me go back to that. Where did it go? Where did I put it now? Let's see. Let's put it down. I'm going to go back here. Here we go. Let me get it back up here. Here we go. There it is. Good. Okay. So let's talk about percentiles here. Because a couple of questions came out about percentiles. A couple of you noticed that when you calculated the percentile for another homework problem, when you did it in Excel, you got a different answer than when you did it in SPSS. That's because there's a few different ways that you might look at calculating a percentile. And SPSS, in fact, built into SPSS, you have some options. There's a default way that it calculates it, but it also has some options on how you can calculate it. You would think that there's only one way, but as we look at this, you'll see that there can be more than one way. Okay, so let's take a look at this. This is this group here. First of all, number one, what's the other name for the 50th percentile? Right, percentile is the percentage of people, the point at which that percentage of people are below that level or above that level. So the 50th percentile, 50% of the people are below, 50% of the people are above. Right, so that would be the median, not the average, but the median. That's the middle value, right? So in this case, if I go over here, there's 45 presidents here. And I've actually kind of like, made a little chart here that mimics this histogram so that we can kind of see how many people are in each group here. So which value would be the middle value? Well, 45 is an odd number. So 23, the 23rd oldest president from either direction would be the middle value, the 50th percentile. So where is that guy? Well, let's see. You got 2 in this group, 7 in this group, 13 in this group. We count the 22. So the 23rd would be in this range right here. It would be in 55 to 59. So that's where that median, that 50th percentile would be. Okay, so now, the 23rd president is the 50th percentile, right? So now that means that the first to the 23rd are the lower 50% of presidents, first to the 50th. So where is the 25th percentile? Well, the 25th percentile is the middle between these two, right? So if 23 in one group, right? So 23 going down, 23, the middle value there would be, let's see, 11 would be the 12th president, right? So the 12th president is going to be, where is he going to be? He's going to be in 54 to 58. So the the president that happens to be the 25th percentile is going to be in 50 to 54. And what about on the other end? Well, let's count down 12 from the top. 1, 4, 4, and 7 is 11. So he's going to be in 55, 59, the 75th percentile, right? So what did I do there? I kind of used a little bit of a cheat. I said the middle president, the middle value is the median, or the 50th percentile is the middle value. And then the 25th percentile is the middle of the lower 50%. And the 75th percentile is the middle of the upper 50%. So that's one way of figuring this out. The other way is that SPSS is used to working with normal distributions. And there's certain rules that very frequently SPSS are not working with data for an entire population. In this case, we're working, it's kind of funky because this is the whole population. That's how many presidents there were. But in SPSS, you're usually working with samples. So if I have 45 people, those 45 people are a random sample from a much larger population if I'm working typically in SPSS. So what SPSS does is it calculates something called the mean and the standard deviation. And it uses those to predict for the entire population what the 25th percentile and the 50th and 75th percentiles would be. That's not the only way it can do it. It can do other ways too. But that's probably what it's doing in the case where it's not getting the same values as you get in your other data. And so I wouldn't worry about that too much. The probably numbers are very close anyway. And uh, 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 the precision on those are not quite as important as some other stuff. Okay, but we'll worry about that as we move on. Okay, any questions so far? Type in every once in a while so I know you're still there. Okay, so, all right, and you can still hear me. Okay, so let me go back to this. Okay, let's see. Using the data provided in student test scores, use Excel to calculate mean. Okay, so on this one, let me see if I can't find that file quickly. I probably have so many versions of this that I'll be lucky if I get the same one that you use. Okay, here's a series of students, and here are their test scores. I'm going to change one number here. I'm going to change this 57 to a 90. Okay, so you're forced to do your own calculation. Repeat this with your own calculation. So, one of the sessions, we have a recording of us going through and calculating the difference between each value and the average, and the square of that, and the sum of squares, and standard deviation, so on and so forth. For this assignment, you're not expected to do that. You can use the values that are built into Excel to do that. The functions are built into Excel to do that. So let's say I ask you to find the mean, the median, the mode, the standard deviation, and the variance, and what else can I? And the range, and the 75th percentile, and the 25th percentile, and the interquartile range were this. And the interquartile range is the area between the 25th and the 75th percentile. You'll see that in the box on box plots, so it's important to us. So what's the mean going to be? It's going to be equal to the average. And we have a function in Excel called average. Whoops. Parentheses. Okay, I'm doing this relatively quickly so you guys can actually go back and do it yourself. You're going to find the average between A2 colon A21, and that comes out to my calculation, 79.35. It's going to be different for you because you work in a slightly different case. So what about median? And there is indeed a function called median. Parentheses, and what's the median? And the median value, the middle value, is 79. Now, it might not be exactly 79 when you do it manually. There might be more, but it probably is. I won't speculate on that. Mode's the most value that comes up most frequently. Kind of like not that useful because a lot of times that really doesn't tell us too much. 79 is the value that happens to come up most frequently, and I'm guessing it's because there is some. Whoops. There is, yeah, 1, 2, 3, 4. Yeah, that could have been 78 also. Notice 2 78s. So you could have more than one mode. It could be multimodal, as we say. We'll take a look at that as we move on in the lesson. Standard deviation. That's a measure of the variability. Actually, let me do the variance first. Oops. Equals variance. Let me see if I. Nope, doesn't need it. It's VAR. Parentheses. And the variance is equal to 53.81. We calculated that the hard way in one of the sessions. And what about standard deviation? Standard deviation is also a measure of the variance. It's a little bit more realistic measure for the variance. That comes out to be 7.3. Now notice something. The standard deviation is just simply the square root of the variance. So we calculated that either way. Now what about the range? The range is the minimum value, the maximum value. Okay, that's maximum value of all of these. There is a function called maximum, close parentheses, minus the minimum value for all of these. You could just do that by sorting them and try and see which one it is. The range is 28, largest to the lowest, highest to the lowest is 28. What about percentiles? There is a function here for percentiles. Equal percentile, parentheses. Okay, now what do I got? I got to tell it the numbers and I got to tell it the percentile I'm looking for. So the array is these numbers, comma, 0.75 for the 75th percentile. And that comes out to be 83. And for my 25th percentile, it's going to be the same array. Remember, I've changed these numbers here, so they're not going to be exactly the same as the answers on the homework. Okay, that percentile, whoops, I forgot. It warned you, there was a little red mark there, 1.25. Okay, that's the 25th percentile, and the interquartile range is the difference between these two. Okay, that's my interquartile range. How many people are between those two values? Okay, and the median, well, the 50th percentile. Let's do 50th percentile. Okay, again, the array, plus comma, 0.5, 0.50 percentage. Okay, comes out to be 79. Look at this, 79. The median is the 50th percentile. So you got the same number there. You did it two ways, got the same number there. Okay, you guys okay with that? Okay, let's move on. Now I'm going to do the same thing, except I'm going to do it in SPSS. Now you've got an SPSS, you may have an SPSS version of this file, right, which I was just using here. I'm going to clear this all out, so I got a clean file. Okay. You may have an SPS version of this that you can import into SPS. You can open in SPSS. I'm going to show you how to import it from an Excel file. Okay, so I'm going to save this, save as, and okay, finally came up, desktop. I'm going to call this student test scores Excel. So that's on my desktop now. Okay, I'm going to close this. Excel does not like to work with files that are open in another program. So it won't let you import it if you try it at that stage. So I'm going to open up SPSS. I hope you guys are having some success getting SPSS installed on your computers. Assignment one, I really want you guys to get started and get that in. Give me at least a submission of that so I know you guys are working and stuff like that. So make sure you submit something as soon as possible on that. Even if you don't have SPSS or you don't have a chance to get to school until Tuesday or something like that, submit it with whatever you can get done so far, and then as long as you submit before the due date or by the due date, you can always go back anytime you want the rest of the semester to redo it as many times as you want until you get 100% on it. So, long story short, if you just keep up and make at least attempt it once before the due date, means that there's no reason for you by the end of the semester not to have 100% on that 30 or 40% of the grade that we're talking about. It's going to say file, open. It's going to say open data. Okay, so now I can navigate and find, look, it's looking for SPSS files, which are .sav files. I can navigate around my computer to find it. I'm on my desktop right now. And I know I saved that file here, but I don't see it. The reason why I don't see it is because I'm only going to see .sav files. So I'm going to click here, and I'm going to either tell it to show all files, or in my case, I'm just going to tell it to show Excel files. And so now I can see any Excel files. There are a couple of Excel files here. Like the one I'm interested in is the one I just created, student test scores.xls. Again, remember, this file is a little bit different than the one you've been working with on the homework assignment. I changed it just a tiny bit, just to keep it a little bit of a challenge for you guys. So what comes up here now is it tries to interpret the data. First thing it tells me is it sees stuff between A1 and A21. That sounds right. There's 20 variables here, but it says the 21. Well, that's because the top line is the variable name, scores. And in fact, it recognized that because it wasn't a number and said read variable names from the first row of data. So that should be checked off. If that's not checked off, it thinks that that word is part of the that it's part of the data, and we don't want that to occur. We want it to understand that that's the data, that's the variable name. I'm going to click OK. SPSS will import it, and once it imports it, I can now go and do an analysis for it. So if you go all the way up to the top here, you can see there's an option called Analyze. I'm going to go Analyze Descriptive Statistics, and if I click on frequencies is usually we use that for looking at categorical data. Okay, you can use it if I want to find out the quartiles and so on and so forth, and the mean and the median. Actually, well, why not? Well, let's do it. Okay, mean, median, mode. A lot of stuff missing there. That's percentiles. Okay, let's take a couple points for percentiles. No, that's not what I don't need that. Percentiles. Okay. Whoops, I can put in what percentiles I want. All right, let's put in 25 and 75. Maybe I should have put point. We'll find out. Okay, I'm gonna move this into the variables box to let it know. Remember, there could have been many columns here which represent variables. It could have been age, could have been BMI. So there's only one there, but it still needs me to move that in there so it knows which one of these to work with. And SPSS comes up. First thing comes up is it comes up with its syntax, the language that it uses to describe the work that it's doing. And in fact, here we go. It came up and it gave me a summary of the mean, the median, the mode, and so on and so forth. The asterisk is there because there's more than one mode, right? It gave me the lower number. Excel gave me the higher number. 78, 79 occurred the same number of times. And the percentiles, it looks like pretty much the same thing. Okay, but there is some other stuff I might be interested in. So I'm going to go here to Analyze. I'm going to go back to Descriptive Statistics. I'm going to go past that, and I'm going to go to Descriptives. Again, basically, I can do the same kind of thing here. Move that in, say Options, Mean, Median, give me the variance. We didn't have that before. Give me the range, right? And click OK, and OK. And now I'll get a bit more data. And you can see it summarized a little bit more neatly down here if that's what you're after. I can go even further and get a lot more detail. I can go to Analyze, Descriptive Statistics, and I'm going to go to the third option here, which is Explore. And in Explore, notice there's a couple extra boxes here, right? Well, for this, for our purposes, we're just going to move this in here, and it's already going to, it's going to do all sorts of descriptive statistics. It's not going to ask me to identify which ones. I can click OK, and now I can get all kinds of interesting statistics for this variable. And where are they? Here we go. There's our statistics, our mean, our median. That gives me a confidence interval. We're going to worry about that later on. It's coming up very soon. Median, variance, standard deviation, minimum, maximum, range, interquartile range, and so on and so forth. So we got a lot more information about that. We also get, we also get a box plot. The box plot shows us the lowest value, shows us the highest value, and it shows us the median. Here's the median, 79. And here's this and this is the 75th percentile. This is the 25th percentile. So this box, the range of this box is the interquartile range, the middle 50% of the test scores. Right? Now, occasionally you might see the feather up here is the highest value, or you'll see another asterisk or some other kind of indicator up above that. That would indicate there's a value that's so far away from these other values that SPSS is warning you that may be an outlier, maybe data that's in error or something like that. You might have to consider whether you want to include it or not. And so that's what you'll see there. So I'm gonna move this out of the way, go back to this, and say that basically what I would be asking you to do is copy those files you just created. Where did I put it? Hope I didn't close it. I don't think I closed it, right? Oh, let's see if we got our output here. Here's our output. All this goes into an output window, right? So if you close the output window, you'll lose this. So you might want to save the output window, or even better, you may want to export it as a Word document. Or you might want to take the files that are in here and you might want to paste them into another document, into a Word document. And in fact, that's what I ask you guys to do. I ask you guys to take okay, that's good. Yeah. Oh no, I don't need a certificate. I hit that too soon. Okay, new blank document. There we go. Okay. So you can take these statistics that you calculated here. So for instance, here's a nice simple one. You can highlight that table. You can say copy, okay, whichever mechanism you want to use, Command C, Control C, go up to the File menu, and up to Edit and Copy, and then you can go over to a Word document and you can paste it into a Word document, like so. Okay. I got my these silly things turned on. Let's turn those off. You could also paste it as a picture, and you could also take your chart that you created. You can say copy, and we can go over here and paste in our chart. Okay. Hopefully, there you go. And when you paste it in as a picture, it's nice because you can resize it and move it around the document a little bit better. Some of you, my installation is a little bit funky, but some of you should be able to say copy, and then that table, instead of pasting it as text the way it went in before, you can say edit, and you can say paste special. And one of the options may come up. It doesn't come up on mine, But one of the options that will come up on most of your installations would be to say, paste as an image, a PNG or a JPEG or something like that. And you can paste that chart in literally as a picture. That doesn't work for you. Whether you have a PC or a Mac, you can use whatever program, like I'm using this program called Grab, to say capture a selection, right? And I can go here and actually copy my table, like so, and save it to my desktop, and then drag it into Word if I want. Do that. And then I can go to my desktop and drag it in. I might even be able to paste it here. Oh, no, still got the old one. Where is it? Okay. Let's see. Go to my desktop. And there it is. Okay, and there you go. It's a picture. It's dragged in as a picture now. Okay, so you can use any of the ways that you have. But then save this, give it a name, upload it for your answer to that assignment. You'll notice that the assignment then waits for me to open and close all those files. I'm going to be doing that probably half the night tonight because I think I've got enough of you guys that have been submitting them now to make it worth going through all of those and correcting them. The PDF on President. Yeah, if you read the problem on there, I mentioned that don't worry about that. I'm giving everybody 100% credit on that problem. It says that in the problem now. So don't worry about it. Just answer anything and it'll give you full credit. That's because the question and the chart don't match. And once people had started submitting it, I couldn't go back and correct it. Some problems I can go back and correct. That type of problem, that kind of submission, I couldn't go back and alter. So hence why I'm going over it now. Okay, so let me move on to the next question. Let's see where I am now. Let's get there. Okay, here we go. All right, so, okay. So that one other thing, there's another file on there called ncbirth800.sab. And it'll be inside, I think it's with your assignment. If it isn't, it's with our sessions also. I'm going to use it probably quite a bit. Okay, I'm going to just pull that up right now. I'm going to open that up in SPSS. Okay, I'm double-clicking, basically double-clicking on the file, and it should open in SPSS as a consequence. I hope. Okay, let's do it this way. Okay, I copied it there. So let's do it this way. Say File, Open, Data, and I'm going to navigate to my desktop. And notice this time it sees it because it's looking for that .sab file. Now, I think I checked. This is different data. Oh, I'm sorry. Excuse me. This is the same data that you're working with. Okay, so I don't remember exactly what I asked you there, and I'm not going to look back and tell. It opened it both times. This is a sample of 800 randomly selected births, data on 800 births over the course of a year in North Carolina, in which there might have been 20,000 or 30,000 or 50,000. So it's a sample from a population. So let's say as a consequence, we want to know what this tells us about the entire population. We want to use the sample to estimate the average for different values here. How many of the mothers were divorced, how many of them were single. So for instance, a number of variables here. In the variable view, I can see that this data has been coded for me. So for instance, if I'm interested in the mother's age, it already knows that it's a scalar variable. Now SPSS gives you the option of 3 different kinds of variables: scalar, ordinal, or nominal. Okay, so nominal would be names, scalar would be any kind of number. Okay, so the mother's age, right? The age of the mother is a numerical variable. The marital status of the mother it's in there as a number, but it's actually a nominal variable. The number is a number which represents the mother's status. And that's coded under values. So if I click on the corner here for by values, it tells me that 1 represents married, 2 represents not married. That's a categorical variable or categorical and nominal variable. Okay, so let's say I ask you to tell me what is the average age of mothers giving birth in North Carolina, right? Well, I could go up here to analyze, descriptive statistics. I could go to frequencies. I could go to descriptives. I could go to explore. I'm going to go to descriptives. I'm just going to move in the age of the mother. So it's going to give me the average age and variance and range for mothers that gave birth in North Carolina based on this sample. And I'm going to click OK. Okay, and here we go. And let's see. Well, it's 800 women, 27. The range 27. The oldest was 42. Youngest was 15. This was some time ago. The average age was 26.92. Standard deviation, and so on and so forth. Okay. This is the question. This is the question you're interested in now, Alicia, this particular one. Okay, so I can get descriptive statistics for all of the women. Okay, this is the average for all of the women in this group. Well, now what if I asked you, what's the average age? Let's compare married women versus unmarried women. Is there a difference in the average age of the unmarried women who gave birth in North Carolina and the married women who gave birth in North Carolina? Well, if I go up here to analyze descriptives, I see that it doesn't give me a chance to separate those two groups out. So instead, I'm going to go up here to Analyze, Descriptive Statistics, Explore instead. So when I open that up, remember those extra boxes that were there? Well, now I can move in my dependence list and tell SPSS I want to work with the age of the mother, right? I want the average age of the mother. And now I want to factor it. I want to break it up. Factor means break up, right? For instance, if you want to factor 36 into smaller components, 36 factored is 6 times 6, right? And 6 factored is 2 times 3, and so on, right? So if you want to break it up in smaller groups, we can move in the variable that we want to factor it by. So I'm going to choose a marital status. I'm going to move that in here. So now SPSS, instead of giving the average age for all of the women in this sample of 800 women, now it's going to break them up into 2 groups. And click OK. And let's see what comes up. And sure enough, here is the average age for the mothers, for married mothers, who's 29, and the average age for unmarried women that were giving birth was 22.65, quite a bit younger. And so it's interesting, right? This is our first statistic where this is live data, this is real data too. Very old, but we've been using it for a little while, but it's actual data, right? An actual sample from the larger population. So boy, it does seem like unmarried women are likely to be considerably younger than married women at the births for unmarried women will be a younger age than married women. So, and we have other data about its variability and so on and so forth. I also now have a box plot. I can see, well, look, it's really obvious now when you see this box plot. So you look at the median age, the middle age for not married women and for married women. Quite a difference, right? Look at the variability here as well. Now look also that the variability for unmarried women is pretty dramatic as well. But the unmarried women tend to be clustered younger, but then we have a lot of outliers, a lot of values that are much different than the median value that we have here. And SPSS kind of highlighted them as outliers. It's up to us to decide whether or not they're really outliers or not, but it kind of highlighted them. And the numbers refer to which subject that was in the data view. So the 105th subject would be, I think it was 105, right? I don't know. There was some one in there was a highlighted. I think it was 105. And how old is she? 37, I guess. Right? She was one of the outliers, or 39, maybe it was 39 or 40. Right? Those are probably outliers for unmarried mothers. So that's what I'm asking you to do there. I want you to understand how you can break these up into different groups, in numerical variable, and then break it up by the values of the categorical variable. If I had done analyze, uh, descriptive statistics explore, and I had said instead of marital status, I had said, I don't know how many values we have for the race and mother, but I'm going to put that in there and click that, see what we get. Okay, well, let's see. We have a whole bunch of results there, right? Because we have white, black, American Indian, Chinese, Asian Pacific Islander, and so on and so forth. So we have a lot of different averages there. So you can separate those very quickly and very easily. Okay, did that answer your question, Alicia? I hope so. Okay, so I'm just gonna get this out of the way. I just want to move on to the next thing here. I want to make sure I catch all of the questions here. Okay, so let's get rid of this thing. And the other homework, B page. Okay, so the other homework was, where'd it go? I thought I had another one of these open. Okay, apparently not. Let's try this. Oh, this is gonna have to log in again. Oops. There we go. I'm gonna log into this one over here. It might be a little bit different, but I log into this. But they should be similar enough. Different due dates. Got different due dates on these things. So don't get fooled by the due dates. Just worry about your due date, not the other class's due date. Okay, that's this one. Okay. I'm going to continue. Let's take a look at this one. So let's see. What do we have here? We have, let's see, prevalence of diabetes in population 10%. You test three randomly selected people. It's probability all three are diabetic. You guys know how to do that right now. 0.1 times 0.1 times 0.1 is the probability randomly selecting three people from this population. So I am going to move on from there. This one's a little bit trickier, but no, it's basically, there's probably none of the first. You'll know how to handle that. Just think back to what we were talking about. Well, some of you guys missed that, didn't you? I didn't get that on the recording, so let me do that now. Prevalence of diabetes in the population is 10%. So if we randomly select one person, chance of they're diabetic is 10%. If we now randomly select a completely different other person, the probability they're diabetic is 10%. And another completely random person, the probability they're diabetic is 10%. So if I ask you, what's the probability of me selecting two separate people and they're both diabetic? It would be 10% times 10%, or 0.1 times 0.1, or 0.01, 1%. What's the probability of all three being diabetic? 0.1 times 0.1 times 0.1, which is 0.001, right? So what's the probability that you select three people and none of them are diabetic? Well, if prevalence of diabetes is 10%, the probability of selecting a first person and not being diabetic is 0.9. So it's probability of selecting three people in a row that are not diabetic randomly, 0.9 times 0.9 times 0.9. It goes out to 0.81 times 0.9 would be somewhere around 70% or something like that. Okay, okay, good. So we did that earlier, but for you guys that aren't here, that I hadn't turned on recording yet when we did that with a coin before. Okay, the top. Okay, so this one's a little bit trickier, but we'll see if you can figure it out. And then Venn diagrams, you can go back over the material, and if you get stuck on those, let's see, I think somebody mentioned, let me see which questions came up. So I'm into question number 3. Oh, that's the one I was hoping to skip. Okay, 60% of the population has completed high school. You take repeated samples of size 3 from this population and find that 22% of the time all 3 students have graduated high school. Okay, does this result suggest that your sample was random and independent? Let's think about this. What would you expect if you took random samples of size 3 over and over and over again, many times? What would you expect the percentage of time that you would get all 3 subjects to have graduated? Well, probability of one person graduating is 60%. Probability of randomly selecting 2 people is 60% times 6.6 times 0.36. The probability of selecting 3 people randomly is 0.66. I don't want to strain my brain here. 0.6 times 0.6 times 0.6. Okay, and that looks like it was going to be about 22%, right? So you say to yourself, okay, sometimes you're not always going to get exactly the outcome you expect. Right? In fact, you can't get 22%. You can only get, like, if you select 3 people, it's either going to be none, 1, 2, or 3 that graduate high school, right? And none of them are 22. None of that's 22%, right? So if you take repeated, sometimes you get 1, sometimes you get 2, sometimes you get 3, sometimes you get none. If you average that, on the average, you would expect to get the outcome that would come from an independent sample. So if you find that it's 22% of the time you get all 3 subjects, if you repeat it many, many, many times, and 22% of the time you get the outcome that all 3 have graduated, well, that suggests that your sample, given that you know that it was 60% of the population who graduated, that would suggest that your sample was independent, right? Your sample was truly independent and random. Now, what if I had told you that it came out that 50% of the time all 3 students had graduated high school? Well, that doesn't fit with taking 3 random samples and 60% of the population had to graduate high school. There's something wrong there. So there must have been something that suggests your sample was not independent, right? But in this case, we know that it was, because it came up the way we expected. 0.6 times 0.6 times 0.6 is about 22%. Okay? So that's what that's all about. Okay, and the Venn diagrams, we know that this is A union B. In other words, all the values for A and B. And we know that that is A intersection B. A with an upside down mean B, right? And, that means that it's both, right? This could be either. This has to be both. Okay, how about this one? Well, this is A, but it excludes any A's that are also B's. So that would be A, right? And let's see, that would be A and the intersection of not B, right? So in other words, it has to satisfy both conditions, right? Intersection means it has to satisfy both conditions. So that would be A and not B. It's got to satisfy both of them. So the only people that are A and not B are the people who are in the shaded part there. Okay, so let's look at testing here. Okay, good. Yeah, let's take a look at this. Whoops. Stay on page. Okay, so now cooties. Okay, that's a familiar. Do they still talk about cooties? When I was a kid, that was a big deal. Cooties, right? Fake disease. You got cooties, make fun of each other. You got cooties and stuff like. Hopefully, kids are a lot nicer than they were when I went to elementary school, but I doubt it. Right? So, human nature being what it is. Okay, so let's say we take a look at this. Prevalence of a condition that affects 10% of the population. Well, that makes sense, because in this population, it looks like out of 1,000 people, 100 of them have cooties, right? This is in the columns, we have whether or not they have the disease, yes or no, and in the rows, we have the outcome of a diagnostic test. Okay, so a newly developed diagnostic test has been tested on 1,000 randomly chosen individuals. 1,000. Okay, so what is the sensitivity of this test? How good is this test at predicting that someone has cooties? Well, out of 100 people in this population of 1,000, with a prevalence of 10%, out of 1,000 people, 100 of them have cooties. What percentage of the time would you expect it to correctly diagnose that? Well, 80% of the time, it got it right, 80 out of 100. So the sensitivity is 80%. Right? Okay, good. So now what about, how good is it at predicting whether someone doesn't have cooties? Okay, in other words, let's say you're among the 900 people that don't have cooties. What percent? What percentage of the time does it correctly identify you as not having cooties? In other words, out of these 900 people, how many of them test negative? And as it turns out, the negative test for people with no cooties, 810. 810 over 900 is 90%. So 90% is the specificity. Sensitivity is how good it is at predicting you have it, and sensitivity is how good it is at predicting you don't have it. So that would be 810 would be the specificity. Okay, so now let's think about that for a second. Okay, so that makes this cell over here true positives. And that makes this cell over here true negatives. Don't have the disease and you test a negative, true negative. You do have the disease and you test a positive, true positive. So what does that make these other two boxes? Well, the 20 people that don't have cooties that are in this box, that have cooties were in this box, tested negative, they're false negatives. They tested negative, but they actually have the disease. What about up here? Well, these people tested positive, right? But they're among the 900 that don't have the disease. So those are false positives. So this is a positive, this is a positive. So the total number of positives is 170, right? But out of those total number of positives, right, we had 107, we have 80 of them actually have cooties, the rest of them don't. So what's the positive predictive value? How good is this at telling us that whether or not, if you test positive, how good is that at telling you that you have cooties? Well, 80 out of 170 people who have tested positive actually have the disease. So it's 80 over 170. So I'll leave that up to you to figure that out. It looks like it's about a little under 50% or so. So I'm going to move on here. Now, prevalence. Okay. So now, one of the things you should realize with this too is that I stopped very simply over here, but there's a lot more to this. Okay, what if the prevalence was only 1%, right? How would this look if the prevalence was only 1%? Well, out of 1,000 people, only 10 of them would have the disease, 990 would not have the disease. So if the test is 80%, I'm going to use the same test, same accuracy. If the test is 80% accurate, 8 people out of 10 would test positive. How about the percentage of people that tested negative? Well, 990 people would be negative. 10 would have the disease. 990 people would be negative, would not have the disease. Out of that, if you got it right 90% of the time, that would mean 90% of 990 is still going to leave 10% of those 99 people as testing positive. The rest will test negative, but 99 of them are going to test positive. You don't have the disease. So now we have 8 people who really have disease test positive, 99 who don't have the disease. That comes out to 106, right? So 9 out of 106. Now your positive predictive value is less than 10%, right? Wow, that's not very good. Most of the people that test positive don't have the disease. A big number of people, right? And that's because it's the same test, 80% sensitivity, 90% specificity. The only thing that changed was the prevalence of the disease in the population. So if you apply a diagnostic, it could be a good diagnostic test, but if you apply it to a lot of people in the population, you may wind up getting, if the prevalence of the disease is very low in that population, it increases the number of false positives that you're going to get. So you have to be very careful with that. And that's a problem with mammograms, with pap smears, with PSA tests for specific antigen, for prostate cancer, and so on and so forth. They tend to produce a lot of false negatives, false positives. Okay, now remember our Bayes theorem? Okay, this is where we're applying our Bayes theorem. Remember before I said the sensitivity times the prevalence? That was the P, B given A, and the PA. That's where we have that up here. So that's the percentage of people that test positive, the proportion of people that test positive and have the disease. And on the bottom is the total number of people that test positive. This is the people that test positive and have the disease, and these are the false positives, 1 minus specificity, 1 minus prevalence. So you can just, if you know what the prevalence is, like on this test, 80% times the prevalence, 80% sensitivity times prevalence is 10%, and get that number, right? That would be 80 times 10, 80.8 times 0.1 would be 0.08 over the same thing, 0.08, the percentage that are true positives, times plus the percentage that are false positives. And you get the false positives from the specificity, which was 90%, 1 minus 90% would be 10%, times 1 minus the prevalence. Prevalence was 10%, which would be 0.9. So 0.1 times 0.9. That would give you the proportion that are false positives. So on the bottom, you have all of the positives, and then at the top, all you have is the correct positives. And that's your positive predictive value. You do it the same way that we did it up here, 80 over 170, and you get the same percentage when you do it this way as well. And so that's our application of Bayes' theorem for this work. Okay, so I'm going to call it a night. I hope this helped a bit.